Good afternoon, Vegas. How's everybody doing today? Very nice. I can see that lots of people are still living because, you know, Vegas. So today I'm going to talk about how to maximize the performance of S3. In this presentation, we're going to provide you some best practices in terms of architecture, how to perform our gets, our puts, and how to leverage the power of other services that AWS provides together with S3. And also, I have here together with me a customer that is going to present to you his use case at the end of the presentation, right? Just make sure, is there any Murphy in this room? No? No, just making sure because I have some demos in the presentation and I don't want Murphy's Law to be my session, so that's fine. Let's roll. So, comparing 2013 against 2014, we had a 137% increase in the AWS S3 usage. That's huge. And we're not including the usage of AWS objects. It means that this increase is being made by you guys. Thank you. That's nice. So here's the agenda of our presentation. We're going to begin with architecture, where I'm going to share with you some best practices on key naming, how to choose the best region to put your objects, and considering lists when using your S3. Also, I'm going to talk after that about how to optimize your puts, okay? And how to use multi-part uploads to leverage the benefits of parallelism. And we have a demo after that, hopefully. And right after that, we're going to talk about how to optimize gets, how to use AWS CloudFront to leverage the power of S3, how to perform range-based gets, and also, hopefully, another demo. And at the end, we're going to have our customer case presented by Big Data Corp to run. So let's begin. Architecture. There are a few variables that we need to take into consideration when we're thinking about start using S3 for certain workloads or to redesign some workload that we already have. One of the things that we take into consideration is performance. And when we think about performance, we need to think about how close this S3 region is to your users or the workload that you are planning to put inside AWS. And also put it as closest as possible at the workload that you are currently running inside AWS. So this is performance. The other things to think about are legal and regulatory compliance, because we have some certain workloads that requires that the data resides inside the country. The data is not allowed to leave the country. That is a reasonable consideration to think about. And also that costs vary by region. So certain regions have lower costs and things like that. Thinking about architecture, one of the most important things that we always discuss with our customers is that naming is king. So if you want consistent performance from your bucket, if you want your bucket to be capable of routinely exceeding 100 TPS, and 100 TPS is a lot, we advise you always to take a look at our public documentation where we have considerations around request rate and performance considerations. There we have lots of explanations and tons of tips about how to create the proper naming scheme and things like that. TPS. What does the acronym TPS mean? TPS means transactions per second. Simple as that. So let's talk about here an hypothetical application where we have a bucket, we have a mobile device, actually hundreds of thousands of mobile devices using your application, hopefully, And we have behind it, also inside AWS, a few EC2 servers running your workers, your application, your APIs, or whatever you need to run to fulfill your application needs. So the mobile application, for example, uploads an image to your bucket, and this image needs to be analyzed or something like that. Then after this image is analyzed, your EC2 workers generated 3 other informations that are put on S3. So far, we already performed 5 TPS against S3. And also, after these 3 new information generated by our workers are put on S3, your mobile application retrieves 3 new information from S3. So to fulfill a single event from your mobile application was needed 8 transactions from S3. So thinking about this application, and from the previous slide where we mentioned that if you want your bucket to deliver to you 100 TPS, in this scenario, if we divide 100 TPS by 8 events, to 8 transactions per second to fulfill an event, in this scenario, you would be able to deliver 12.5 events per second, okay, without doing nothing, okay? Just using the regular S3, okay? And when your application reaches something like 100,000 users at 10 events per hour, you would require from your bucket 224 TPS. Whoa. That's time to think about, review your naming scheme, and see and make sure that everything is correctly set up. And that's where the previous slide where I pointed you to the public documentation that we have on the AWS website comes handy, right? So let's talk about distributing your key names. Usually we see something like this, okay? Please don't do this. Don't put a consistent naming scheme in front of your object. We advise you to never ever do that, okay? Even if you're expecting your application to not deliver higher throughput or something like that, if you can rely from the moment 0 in your application using the best practice, use them. If you do this, this is going to happen. The previous application that I mentioned, your application starts growing, okay? Then you have your workers behind the scenes, your mobile application working. Then you have your bucket partition by AWS. And when the transactions starts coming from your mobile devices to S3, this is going to happen. Due to the bad naming scheme, all of the transactions are going to hit the same partition. And this is not going to deliver you the expected throughput. So you start to suffering from the throughput, okay? So what we advise is add some randomness to the beginning of your key names. When you do something like that, as you can see, we have random numbers, random algorithms at the beginning of our key names. Behind the scenes, if you take a look at the same application, all of your transactions will be able to be distributed evenly across the partitions. So you have your partitions, and the transactions you'll be able to hit different partitions during the occurrence of an event, okay? Also, we can talk about other techniques to distribute key names, not only adding some random names at the beginning of your keys. Usually we have some customers that store objects as a hash of their name. So they just take the object name, compute a hash over the object name, and store the object as the computed hash. This is a very reasonable way of storing objects in S3. So using the example that we have over there, the dead mouse and the line mix MP3, you would store this object as something, this long string that we have over there. Also, you can use the option that we gave you guys in the previous slide, calculating some hash using the object name. Then you take the few first shares, something like the 4, 5, or 6 first share from the generated hash. You prepend the generated hash in the object name, and then you store it in S3. Is also a viable option. And also, we have the epoch time reverse. So you just take the current time, reverse it, and prepend to the object name. Is also another viable option. But this is good. This is awesome. But sometimes, using this can be an anti-pattern. When you have to resort to lifecycle policies, or list with prefix filters, or maintaining thumbnails of images, or when you need to recover a file with its original name, it can become a problem. But no problem, you're not alone in there. We have a solution for this. You can prepend to the object name what we call a folder. We can put a folder and put the randomized object name inside this folder. This way, you're going to be able to the benefit of transactions per second that S3 is going to provide you by adding some randomness at the beginning of your objects. But also, you would be able to still resort to lists and other operations in your S3 bucket that needs to rely on the name of the objects that we have. So, like I told you guys, distributing key names, even when you think you don't need it, it's always a good idea, okay? Even when you're using the best practices, it can take some time to S3 to reflect the changes that you made to your bucket, okay? And like I told you, 100 TPS is a lot. That's a lot of transactions. To exceed 100 TPS, it's a lot. But even so, in case you expect more than that, once again, the documentation that we have on AWS has tons of tips for you guys to create the best naming scheme for your use case scenario, okay? And you're not alone. When you're reviewing any design that you already have, or you're planning the design of the new application that your company is planning to launch on the market, or you have some crazy idea to create a startup, anything, you're not alone. Like Werner Vogel said today in our presentation, AWS is not just AWS. We are much more with our partners and our marketplace. So before starting to create something from the scratch, please take a look at our marketplace, okay? And see if we don't already have any other solution that can fulfill your requirements, okay? And for any solution that you find on the AWS Marketplace, you don't have to start paying from the moment zero. Almost all of them, they provide you something like a free trial period that you can start using without paying nothing. And some of them provide some like freemium. They provide their product, but with less features and something like that. And you can pay everything together in your AWS bill. You don't have to worry about that. So we talked about architecture, so let's talk about now how to optimize for puts. Usually when you're putting objects into S3, you just use the regular SDK, the console, the CLI, whatever, and you're putting objects into S3. But usually when you're using the SDK, people are resorting to the standard way of putting objects into S3. They're not using the multi-part upload, okay? And here I would like to talk about with you guys about the benefits of parallelizing your puts, okay? When you parallelize your puts, you are able to increase the aggregated throughput by parallelizing your uploads on higher bandwidth networks. And when you do that, you're able to move the bottleneck to where it belongs, the I/O bottleneck to where it belongs. So it goes to the network. Network will take care of that, right? And also, when you use multi-part uploads, let's say that you're uploading a 1 gig file to AWS. If you're doing it in the standard way, if in the middle of the transaction the upload fails, you have to start it from the scratch again. So you lost all of the bytes that you already uploaded. And using multi-part uploads, you can benefit from faster and flexible uploads. You can break your object into a set of parts and upload them sequentially or parallelly. And after all of the parts are into S3, S3 is able to present all of the parts together to compose the original and single object. And another cool benefit of parallel uploads is that it allows your application to pause and resume the uploads of your objects. So that's very nice. So if you have to upload, again, the same example, that 1 gig file, and you are at the moment that you already uploaded 500 gigs, 500 megabytes, you can pause the upload and resume transferring the other parts afterwards at any moment that you want, right? But when we talk about multi-part uploads, we need to think about how do I choose the minimum part? We always advise your customers to start with parts of 25 or 50 megabytes when we're talking about higher bandwidth networks. But when you're considering your mobile applications, you should start trying with 10 megabytes or so, something like that. This is not a rule of thumb, right? But this is a good start. And also, you need to strike a balance between the part size and the number of parts. Because if you increase the number of parts, you won't benefit of the multi-part uploads because you put too much overload on your network. And if you're uploading fewer parts and larger in size, you also won't benefit of multi-part upload because if the upload of one of the parts fail, you will have to transfer a larger part of the object again. So we always recommend benchmark for your scenario. And S3 also provides you the option to use encryption when you're transferring, when you're using the HTTPS endpoint. So when you're using SSL, you're likely to become CPU constrained because the encryption itself uses CPU power. Encryption is a CPU intensive process. So Amazon S3 recommends that you, whenever you need to use encryption on your files, use AES-256 to optimize for both security and performance, and to not become CPU constrained in terms of encryption. You can leverage the power of AES and hardware on your host to improve the performance. We have tons of EC2 instances that already provide this benefit, so you can use them to leverage the response times in your application when you need to encrypt the files. So, showtime. Let me present you here a quick demo. In this demo, it's a very simple demo where I create a dummy file with 500 megabytes. And in this file, I will break this file in 20 parts. So it will upload each part having 25 megabytes to S3. Actually, the first one is using 10 parts. So the first task, we are uploading a 500 megabytes in 10 chunks sequentially. So it's doing one part after the other. Let's see how long is it going to take to transfer a 500 megabytes file to S3. if Murphy isn't doing nothing right now, it should complete. Oops, completed. So that's a little gain, right? Almost, what can you say, 700% or something like that. So to transfer the same exact file in 10 chunks using sequential uploads, it took 21 seconds. And the same file using parallel uploads, it took 3 seconds, just 3 seconds. And what I was telling you guys about benchmark for your best case scenario, let's try to transfer the same file again, but using 20 chunks, not 10 chunks. Let's use 20 chunks. And let's see what happens in this case. "20 seconds never took so long." Murphy's working. Okay, so it varies. Probably do it some network variation or something like that. But as you can see, using 10 parts, it took 21 seconds in sequential and 3 seconds in parallel. And the same file using 20 chunks, we increased the time from 3 seconds in parallel to 5 seconds in parallel. So that's why we always advise you, benchmark for your use case. You start with the numbers that we suggest you guys and then adjust up or down according to your scenario, right? Good. So let's talk about how to optimize for gets. There's a few ways of how to optimize S3 for gets. You can leverage the power of our content delivery network called CloudFront, where we have, if AWS didn't launch any other POP, I believe it's 55 edge locations around the world. So you can use CloudFront in front of your S3 bucket to distribute your content using the nearest location to your user. So it will speed up a lot the distribution of your content. Okay. S3, CloudFront basically caches the objects of S3 that you are transferring in the nearest location to the user. So it will provide a faster and reliable experience to your user, right? And you also reduce the number of gets that you issue against S3, because once the object gets cached in the nearest edge location, you will save a few round trips from CloudFront to S3, from the user to S3 actually. Okay? And CloudFront provides low latency endpoints. So downloading the same object from S3, even if the user is close to the region that you have your S3 bucket, using S3 or CloudFront will provide, using CloudFront instead of S3 directly, will provide a better experience for your user. And also it provides a higher transfer rate. And CloudFront, you can use it to distribute content from S3, not only images or static files like JS files, CSS files, or whatever static files you're putting on S3. You can use also CloudFront to distribute live content or on-demand video content. So let's present another demo for you guys where I show the difference in performance between S3 and CloudFront. Basically, in this demo, I'm going to issue 5 gets basically against S3 and 5 gets against CloudFront to the same object. And here you can see the difference. Oops, wrong demo, sorry. This is it. So I'm basically trying to get a 1 MB sample file from S3, and it took 3.8 seconds, 3.6 seconds, and now 5 seconds. 2 more times. And you can see the difference between downloading the file from S3 and downloading the file from CloudFront. That's another huge gain. So always try to consider using CloudFront in front of S3 to download the files that you need from S3. But also, when you talk about gets, you can parallelize your gets too, because the same way you parallelize multi-part uploads, you can parallelize your gets. And you can benefit from the multi-threaded performance for downloading objects from S3. And the same benefits that you gain when you use multi-part uploads using range-based gets, you can compensate for unreliable networks. And you benefit for multi-threaded parallelism. And just make sure that you align your ranges with your parts, okay? And let's show another demo for you guys. In this demo, I do the same thing that I did for the multi-part upload, but I do using range-based gets. So the same 2 objects that I generated with you guys in the same demo on S3, now I'm going to run this demo, and we will try to download these objects using sequential and parallel gets. So let's do it. So first, we're trying to download 500 megabytes object in 20 chunks. Sequentially. So it took 9 seconds. So that's a huge gain. Again. So imagine bringing S3 with range-based gets and CloudFront to your application. The huge gains that you can bring to your application, to your end user experience, that's very nice. But also, when we're talking about getting content from S3, there's another operation that is heavily used called list. So sometimes you have to get the object that your customer stored, see all the lists of the file that are storing on S3, getting a list of logs, viewing inventories, or things like that, starting keys based on metadata. What should you do in this case? You can also parallelize your list operations. If you have a list of your keys, you can parallelize them and benefit from the same gains from multi-part uploads and range-based gets. But also, what you could do a secondary index. Instead of relying on the S3 list operation, which is a heavy operation, you could use a secondary list. And a secondary list is able to provide you sorting by metadata, search, and have objects by timestamp. It provides you features that the plain S3 list operation is not able to provide you. So inside AWS, we have a few services that can help you guys to bring the power of second list indexes into your application, either using DynamoDB, RDS, Cloud Search, EC2, or any other database or solution that you might have running inside of EC2, whatever you like. But when you use secondary indexes, you don't have to rely on S3 for the heavy list operations that we have, and you can bring lots of features that the plain list operation don't offer, right? Thank you guys for your time. I'm going to leave you with Toran right now, that he's going to explain his use case about all of the practices that we talked during this session and explain to you how he started and where he is right now. Thank you.
Hello. Hi, everyone. Good afternoon. I'm Toran, And I'm the founder and CEO of Big Data Corp. We're a company based in Brazil. We've been in the market for about 3 years. And our focus is mostly on data capture and data generation. So we do a lot of crawling, a lot of things like that. And that sort of directly ties into the problem that we were facing and how we used S3 to solve it. So basically, we have a very large-scale crawling process where at least once a week we're hitting tens of millions of websites and capturing the HTML content of these websites. And this generates hundreds of billions of web pages. And that amount of data is pretty insane to handle. It's about 500 terabytes per week of raw data that we generate and have to process and parse and do things with. And for a while, we were trying to work with databases and trying to do some stuff with it, and it really wasn't working out very well. And it's interesting for me because it's a very different use case from what you would normally think about S3, because usually when you're talking to people about S3, they're talking about, okay, let's upload a file and then we'll stream it out or send it out to several users. We'll have static files that people are downloading multiple times. In our use case was actually a little bit different, because instead of doing a lot of getting on the file, instead of getting the file several times and distributing it to a lot of users, we had these hundreds of thousands of distributed put requests. You know, we were saving a ton of files, we were saving a ton of objects into S3 that we then needed to do post-processing and work with. And so we started out, we read the documentation, we got in touch with the guys at AWS, and we were discussing with them our idea. And we started working on it, and we started building an architecture for it. And once we started testing it and actually running some test processes with it, we found out that it wasn't working at all. When we originally started out, our idea was to store each individual HTML page as a single object on S3. And if you look at it from a post-processing standpoint, that actually makes a lot of sense. Because if I have each page's individual HTML stored on S3, then I can apply EMR or any other of the services to really process that data really easily and do a lot of fun stuff with it. But that was actually kind of an issue, because we were trying to do billions of put requests and over 300,000 simultaneous put requests into our S3 buckets. And when you consider, Felipe was talking about when he started the presentation that S3 can easily support 100 transactions per second. We were a couple of orders of magnitude above that. And that kind of became an issue. Actually, the first time that we ran the process, we got an email saying, "Okay, you're kind of doing, you shouldn't be doing what you're doing. Let's sit down and talk and try to work out what you're trying to do here, because that's not going to work." And it's understandable, right? I mean, we were using name hashing based on GUIDs. I don't know how many of you are familiar with it, with GUIDs. I think they are sort of they were sort of the default mode for generating a random number to put in front of the key name. So we thought, okay, so we should be pretty safe there. And just putting the data there, and then when we needed to process it, we would run our processes running list requests to get all the file names and the object names that we needed to process and trying to work with that. And as I was saying, that really didn't work out. Even though we were getting a decent compression rate, and even though we were getting some results, it quickly became obvious to us that that wouldn't scale. And that wouldn't scale on a performance, but that also wouldn't scale on a cost perspective. And this is something that we really don't think about when you're doing a lot of puts, that's something that you really need to consider, because put requests are quite more expensive than get requests. And when you multiply the price of a put request by the number of puts that we're actually trying to do, we would be paying about $500,000 a month simply to perform those put requests. And that's kind of untenable in the long run. So we had to change our architecture a little bit, and we talked a lot with the guys from S3 and with the guys from AWS about that, with the architects and everyone. And we ended up changing our architecture to, instead of store each individual page as an object in S3, we actually decided to store each individual website that we were crawling. So we built a more complex object structure in order to actually reduce the number of put requests and afterwards the number of get requests and the number of lists that we had to do on top of that. And that actually brought with it a lot more side benefits that we really didn't expect when we started out. So first of all, we had a huge gain in compression. So we started out when we were compressing the individual pages with about 65% compression rate for the individual web pages. But once we started bringing all the web pages from the same website together and compressing that as a whole, we actually ended up with 90% or even more than that compression, which really makes a dent when you're talking about storing millions and millions of websites. We changed the naming scheme. So once again, naming scheme is crucial, and it's one of the most important things for you to work with. GUIDs are actually a lousy choice for you to randomize your names, because GUIDs usually start with the same prefix or a very similar prefix if you're generating them sequentially. So that ends up destroying the name scheme. It results in pretty much the same problem that Felipe showed with using the date as the year of the date, that you end up hitting all the same partitions and you have a problem there. We actually were able to bring down the number of put and get requests that we needed to do from these billions and billions of requests to a few million or a few tens of millions of requests. And we actually got much better put request distribution, because we only have to save a website once we are finished crawling it. So we didn't have all these individual objects trying to be written at the very same time to an S3 bucket, but rather we got a distribution over time, because individual websites will have different numbers of web pages. So it's much less likely that we'll have all of our distributed servers trying to write to our S3 bucket at the same time. So that really improved performance as well. And the last thing that we did in order to improve the results and improve our process was to start working with secondary indexes. And that was not only to reduce the number of list requests that we wanted to do on top of the data, but actually to allow us to perform more complex operations on top of the data that we wanted to store. So we are storing our secondary index in a database that carries with it a lot of metadata about that object that's stored on S3. So that allows us to do all sorts of segmentation before we actually go out and read the object. So I can take all the individual websites and I can say, okay, let me only process the websites whose domain name ends in .com.mx or something like that, and I can read only those objects, and I don't have to list my bucket and look at the individual objects to know that, because that's stored in an auxiliary database, and that database has the pointers to the objects inside S3. So that really helped us out further along the path. Just to show you guys real quickly, this is the architecture that we operate today. So basically we have a reserved instance that orchestrates the entire process. We use SQS to do all the messaging between the individual processes. And every time once we've crawled the web page, we'll store the raw data the raw data for the websites on S3 compressed with the structure that I mentioned. And we'll store the links to the IDs of the objects and all the metadata associated with them on a MongoDB cluster, which allows us to do all the segmentation and the filtering that I was mentioning a little bit earlier. So just to quickly go over these things first and foremost, pay attention to the naming scheme. It is really, really important. It's really important not only to make it easier for you, to avoid all the transactions hitting the same place, but also it makes it easier for you to work with the objects later on, to apply policies to them, to delete a ton of them at the same time, and to do those things. GUIDs are terrible. If you come from a Windows background, as I do, we're used to using GUIDs as IDs for a lot of the things that we do. And that's a really bad idea when you're dealing with S3 because the first characters tend to always be the same. So you're always going to be incurring that problem. So we actually built a special randomizer that generates the first 4 letters of the objects that we want to store. This is really important. And then using the secondary indexes instead of listing the objects. It allows you to do the segmentation. It makes it much easier for you to do parallel processing, especially if you're running a large-scale process on a ton of servers and you can simply grab down those objects, or you can put the name of the objects on the queue from the database and then work with it. You don't have to be running list commands against your bucket all the time. And it really makes the code simpler. And since it's simpler, it's easier to maintain. It gives you a lot less headaches. It becomes much easier to work with. And once again, puts and lists are a very easy to overlook expense. When we designed our original architecture of storing the individual web pages as objects on S3, we really didn't stop and do the math on the amount of money that we would be spending on put requests. And that was a very, as I mentioned, that was a very bad idea for us, because once we actually sat down and put it in the paper, we figured out, okay, this will be completely, nobody would be happy with us, right? Amazon wouldn't be happy with us because we wouldn't be able to pay our bill at the end of the month. We wouldn't be happy because, we would be out of money to run the company. Think about what you're trying to do. Think about the puts and the list requests as well, especially if you're doing processing that's not related to distributing files to a lot of people. That's something that's really important to look at. And one other thing that's actually not on the slide there is something that Felipe mentioned earlier, that you should always keep your data as close to the processing place as possible. I mean, we talk a lot about CloudFront and putting the data close to the users, but in our case, we're not actually sending the data out to any users. We're using it internally. So we have to keep it as close as possible to the region. If I'm going to use S3 in the same region where I'm going to host my servers, and that can lead to a 5 to 10 time performance gain when you're accessing and working with that data. So it is really important for you to keep the data close, not only to your users, but to where you're going to run your processing on it. And with that, I'm going to hand it over again to Felipe.
Thank you.
Thank you.
So thank you, guys. Wrapping it up, we talked about our architecture on top of S3, how to use our best practices and tips to, optimize the performance or maximize the performance of your S3 usage. And we talked about how to optimize for puts, for gets, and we had the customer case of Turan. Here you have our contacts, and we'll be happy to talk with you outside. We're going to have a QA station over there, so if you have some questions for me or you're interested in Turan's case, just come to talk to us outside. Thank you.